Welcome to the third session of this year 2025. Today evening we have a very interesting session on underwater navigation and communication systems for unmanned and manned vehicles. We welcome the chief guest of the day, Dr. G. Ramadass, ex-director NIOT, and this Professor C.S. Kumar, who will be the session chair. And today's expert presentation will be by Dr. Bala Jyothi of NIOT. It's my privilege and pleasure to introduce our session chair, Dr. Cheruvu Shivakumar. He was born in 1966 and is currently a professor of mechanical engineering in the Department of the Indian Institute of Technology, Kharagpur. He works primarily in the areas of robotics and intelligent systems, and also professionally in the area of CAD/CAM, additive manufacturing, and computer networks. He received his Bachelor in Technology degree in Manufacturing Science and Engineering in 1987 and his doctoral degree in Mechanical Engineering in 1995 from IIT Kharagpur. He briefly worked in Mrs. Godrej and Boyce for probably sometime in 1987 before taking up his PhD, and was a postdoctoral fellow of the Science and Technology Agency at AIST, that is a former electrotechnical laboratory in Tsukuba, Japan in 1999. His research areas span controls of robotic systems and digital manufacturing systems, more specifically in directed digital manufacturing of metals using additive processes and in computer networks. He is currently involved in multiple interesting research projects of national importance that are funded by the Government of India. There is biomedical robotic device development for post-stroke rehabilitation under IMPRINT scheme, supported by MOE and ICMR. MOE project on virtual labs, biomimetic autonomous underwater robotics for NRB, DRDO, and is receiver development for autonomous navigation using NAVIC with ISRO and a few more. He is a member of the professional international organizations, that is IEEE, ASME, and national societies like the Association of Mechanism and Machines, the Robotic Society, etc. In India, he is serving in the national bodies as an expert member in the Marine Systems Panel of Naval Research Board, as an advisor for the Additive Manufacturing Society of India, and member of Telecom Engineering Center Working Group on QoS networks. He served on the IEEE Access Editorial Board and also as an editorial board member of Sadhana. He also serves as an expert panelist in DST, DTB, media for various projects. He has over 150 archived publications in various international journals, conferences, and book chapters. Some of his research and development works got his institute 9 written patents, and another 4 are in patent pending stage. This is welcome, sir, Professor Kumar, and thanks for accepting our invitation to chair this session. Now, we request you to take over the session for the day.
Professor Kumar. Thank you, Dr. Bharadwaj. It is a pleasure. Thank you for the introductions. It got pretty long. It's a pleasure to be on this Institution of Naval Architects seminar technical session. It's an organization which has amazed me, though I'm not a member of it, but I know the kind of good work it is doing, grand work it is doing. And I'm really pleased to be here this weekend to listen to a very nice talk that has been listed as underwater navigation and communication systems for both for unmanned and manned vehicles. I can say from my experience, it's a very challenging topic, and obviously, I'm sure many people will be interested in listening to this talk. So it's at the outset, it is first my duty and privilege to introduce introduce the chief guest of this session, and I'll read out his profile, which is a very interesting profile. Dr. G. Ramadass is known to many for several years, but I know that there are quite a few people who are probably in this session, in this one, who would like to get a more proper update, recent update. So I will go through this one. So Dr. Ramadass is a former director of the National Institute of Ocean Technologies at Chennai, which is under an autonomous body of the Ministry of Earth Sciences, the Government of India. His research areas were in deep sea technology, deep sea mining, underwater acoustics, and marine instrumentation. Instruments and instrumentation. He had coordinated a project on the development of the Indian manned submersible, which many of you have heard, the Matsya 6000. It's also in the news, which is intended to carry 3 scientists and engineers to 6,000-meter depth in the ocean. And since he's been there since the inception of NIOT, and he has been leading various different technology development projects. For instance, in 2010, he did, and he for in recognition of his work, he got the National Geoscience Award under the exploration of oil and natural gas category, and the NRDC award in the year 2017. He led an NIOT team during the 34th Indian scientific expedition to the Antarctica in February-March 2015. He was also, the vehicle that he took that time was called the Polar Remotely Operated Vehicle, in brief PROVE. It's a nice abbreviation, which was developed indigenously at NIOT. And it was used for exploration in the lake, the shelf of Antarctica during this expedition. He has a doctorate from the Indian Institute of Technology, Madras, and his MSc from IIT Kharagpur. He he handled several technology development programs leading to products and patents. He has been the chief scientist of several cruises and scientific exploration on board of various research vessels. He has a number of publications in the international journals and international conferences, and has both national and international patents as well. So with this, I think we are. He has a pretty long list of this. In his patents also is in publications, he has 75 research publications in peer-reviewed journals. He has 15 international and national patents. He has published 4 books, and as we could see, 3 awards in R&D. With this kind of experience, we are really happy to have him here as the chief guest. I thank profusely thank him to accept this and be present today.
Thank you, Professor Kumar. It's my pleasure.
Thank you. The next part of my duty of today is to introduce the others, the key speaker of the event, an expert presentation, which all of you are looking forward to, and that is by Dr. V. Bala Naga Jyothi. She is a very emerging scientist who has been adding to a lot of interesting developments that are related to underwater exploration, navigation, control, communications. Many of these are all based on acoustic technologies. And I'm happy to see that she's making a good presentation on this topic. So before she starts, it is my pleasure to introduce her. Dr. V. Bala Nagajyoti is currently a scientist E in the National Institute of Ocean Technology, India. She is also the associate project manager, realizing the electronics, navigation, positioning, and communication systems for India's indigenously developed deep water manned scientific submarine, which is called Matsya 6000. And also many other unmanned remotely operated vehicles. prior to NIOT, she had an interesting experience also as a scientist engineer in the Indian Space Research Organization, ISRO, for control and automation of the cryogenic propellant systems of geostationary launch vehicle at the Satish Dhawan Center. It's called as SHAR, and also on the attitude on-orbit control systems of geostationary Indian national satellites at the Master Control Facility, Hassan. Her research interests include autonomous guidance and navigation guidance, navigation systems, and situationally aware digital twins. She has published more than 40 papers in index journals, international and national conferences. She holds one national patent. She is the awardee of the Outstanding Woman Research Award of BIWA in the year 2025. She is the member of the Ocean Society of India, an editorial manager of the Marine Technological Society, and a member of IEEE. I know it's a very short introduction, but it's probably too short to do to say what good work she is doing. And we are all looking forward to um, the presentation. So after
Thank you,
this,
sir. Thank you very much.
please take over. We'd like to hear from you.
Yeah. I will share the PPT. Are you able to see, sir?
Yeah, we can see it, yes.
Okay.
Yeah, we can
So
see.
thank
I
you for
hope the
the
audience will also
this
get to see it.
thank you for the Institution of Naval Architects for giving me this opportunity. And I'm going to present today on underwater navigation and communication systems for NIOT developed unmanned and manned vehicles. So NIOT comes under Ministry of Earth Sciences, Government of India, and it is having almost 10 institutes, sister institutes under this Ministry of Earth Sciences, and we are part of this. We are under Ministry of Earth Sciences, where ocean technology, we will be developing the technology for the Indian Ocean for exploration, inspection, and many other applications. And here we are having many departments where NIOT is driving the blue economy of India. So here comes energy and freshwater, where the freshwater is given using thermal desalination technique in Andaman, Nicobar Islands, Lakshadweep, and Kavaratti, in many islands. And coming to offshore structures, they will be working on the structures to be built on the oceans, actually offshore. Then ocean observation system, this is like tsunami early warning systems, and data buoys, omni buoys, data will be telemetry via satellite, and continuously ocean parameters will be observed. Then marine biotechnology, they will be working on the development of drugs from the deep ocean creatures like that. And they are also developing on the fish culturing techniques also. And ocean electronics, they are working on the drifter buoys and profilers for data collection around the Indian Ocean. And ocean acoustics group is developing on the ambient noise recorders and analysis of the habitants in polar and Arctic and Antarctic regions. In that way, coastal environmental engineering group working on the offshore EEZ zone, protecting the dredging operations, then port protection and all, they will be working. And coming to the gas hydrates, this is actually one more like a methane, one more resource, carbon resource is there in Krishna Godavari Basin and Andaman and all. So they that also will be working on the exploration of the gas hydrates. And our group comes under the deep sea technology. I'm working under this group where the underwater vehicles are being developed for deep water, shallow water, and many applications. And we also have the vessel management group where we are having NIOT is having 4 vessels. So we'll be managing for our all we will be going with our vehicles in the ships. And today's talk, what is the need to develop underwater vehicles? What are all the environmental consideration in the vehicle design? And what are the different types of underwater vehicles? And what is a conventional navigation system architecture? And what are the sensors used for navigation, underwater navigation? And limitations in precise position computations? And acoustic positioning system principles, and acoustic communication system and its environmental challenges, and realization of underwater navigation systems for NIOT vehicles. And we are also working on the bio-inspired navigation and homing guidance techniques for AEV, which is very important for autonomous vehicles to for more endurance. Then I just want to give a brief on requirement of autonomy and swarm robotics and AI-based systems for strategic applications. So coming to the importance of ocean, why the vehicles are needed? Because oceans are a source of living resources like seafood, biotechnology, and then hydrocarbons, minerals. When you speak about the Central Indian Ocean Basin, so the mandate is to explore the Central Indian Ocean Basin, how many the manganese nodules, how much is there. So everything we cannot go and see. So we need the vehicles to just explore in the oceans. And these oceans are also a means of mass transport actually. And any cable laying also, cable what is this, crude oil pipes and all also to be laid. And then weather and climate, if you see 90% of the solar energy is stored as a heat, and this is regulating the climate, and oceans produce half of the oxygen we breathe actually. And if you see that the green homogeneous gas emissions also, the cumulative is 2000 gross tons, which remain in the atmosphere, and while 30% have got sink in oceans. So we have this even, we have to monitor the continuously surveillance of cyclones and tsunamis. And if you see this exclusive economic zone, to augment food, energy, water, and mineral resources from EEZ zone, and the enlargement of present EEZ from 2 million square kilometers to about 3 million square kilometers. And there are many technological challenges to harvest the resources in deep waters. And it is a rich source of food, non-renewable energy like hydrocarbon, oil and gas hydrates, and also renewable energy like ocean thermal energy conversion, wave and tidal, and minerals. So cobalt, nickel, copper, manganese, these and all huge squares, lakhs of squares of kilometers are there in the CAOB basin, Central Indian Ocean Basin. That and all we have to explore, and we have to bring to the shore. And freshwater also is unlimited, generation of freshwater. So if you see our deep ocean sites for exploration, so this only I was saying about the Central Indian Ocean Basin, which is at 5,500 meter depth, we find manganese nodules. And one more potential sites is hydrothermal sulfides, where there will be like a sulfide volcanoes will be erupted at 3,500 meter depth. And this is actually placed near Rodriguez Triple Junction. So there actually, if you see near the sulfide sites, some microorganisms like habitants will be surviving at a high temperature, 400 degrees centigrade and 4 degrees degree temperature. So how this is happening? To see with our through robotics, we need some vehicles to go under the depth. And this, we also have the gas hydrate site and the Bay of Bengal. So this is a Krishna Godavari basin. This also we have explored, we have found the potential gas hydrate sites. So NIOT is manned and unmanned vehicle ecosystem. Actually, here comes our first developed deep water ROV. Our former director NIOT was group head for us. Actually, this project was taken up. So in 2010, actually CAOB exploration trails were done, and it went up to 5,289 meters. From the shallow water to deep water, 44 dives has been done, and this vehicle has gone for many Krishna Godavari Basin site and CAOB site, and many inspections were done even torpedo, Varnastra torpedo recovery also was done using this deep water ROV. And here comes the shallow water ROV, where I joined in 2012 at NIOT. And this is my first project where I have worked, which is of around 200 kg. And why the requirement to go for shallow water is for coral explorations and shallow water requirements. We cannot take this huge big ROV because it is almost like 7-8 tons. So there was a need from biodiversity, marine biotechnology to develop to have a small vehicle where the visuals can be explored and biodiversity can be studied during the natural calamities and all. So this is a 500-meter depth rated AUV. And this is called as shallow water ROV and polar ROV because this has gone for Antarctica. This is developed for Antarctica climate conditions suitable. And I will be showing that what and all we have done for the polar explorations. And then autonomous underwater vehicle. This is actually we have procured from Kongsberg, Norway. And this also has gone for almost 11 dives from CIOB basin, RTJ junction, Krishna Godavari basin, gas at risk potential sites. And this also has gone for inspection of the AN-32 missing aircraft. That also I will be detailing in the next slides. And here comes our human manned submersible and the Samudrayan mission deep ocean mission. This is our indigenously developed manned submersible called as Matsya 6000. And recently wet test done in Jan to February 2025. And so this is actually we will be going for deeper waters, maybe in 2026 to 2027. And here comes our deep water coring system. This is actually for exploring of the gas hydrate site in Krishna Godavari basin, where this will sit on the seabed and the core will be taken from at the 1000-meter depth actually. So this one is a deep sea in situ soil tester. So before launching any vehicle in underwater, we will be checking the bearing strength of the seabed. So this vehicle will go and check the bearing strength. Accordingly, the landing systems will be developed with the soft bed locomotion and all. And this is the integrated mining system. This is actually our other group under deep sea technology system, deep sea mining. So recently they also have completed like a 1000-meter depth sea trials in Andaman and collection of nodules. But the target is to go for CAOB to collect the nodules and bring to shore. So challenges in deep ocean. So everyone, I think all attendees are aware of the underwater challenges because every 10-meter water depth when we go inside, 1 bar pressure will increase. So 6000-meter depth rated vehicle means the vehicle should tolerate up to 600 bar. So the structure should be should have the capability to tolerate up to this pressure. And temperature also, it will reduce from atmospheric like 35 degrees in the shallow water surface of the ocean to 4 degrees in deep ocean. After 1000 meter, it is almost 4 degrees centigrade. And communication. So if you, I think everyone is aware that electromagnetic signals, radio frequency signals cannot propagate in ocean because of the water conductivity. So they cannot. So we have to depend on other communication techniques. That is nothing but acoustics, but it's having its own challenges, which I will be explaining now, which is having a low bandwidth and low data rate. And the position determination. Here, like in our terrestrial application, GPS will not be there to get the position of the vehicle. So we will be working on the acoustic underwater acoustic positioning system, which is called as underwater GPS. So that is also has challenges. So which I will be explaining now. Then corrosive seawater. So we'll be having the sacrificing anode for the structures when it goes into deep water for longer time. So the structure should not get affected. So under various sea states, hydrodynamics also is very important of the vehicle to have a less drag when during the maneuvering and all. So, and we will be depending on artificial imaging systems because a completely absolute darkness greater than 10 meters, sunlight cannot penetrate in ocean after, and it will be pitch dark. So, this is as of now our understanding. Since still more challenges are there, where whenever we go for sea trial with all system readiness, new challenges we will be seeing. So, we are learning in each and every sea trial. So coming to the environmental challenges in underwater vehicle design, so hydrostatic pressure tight and enclosures, everything required, and feed through the continuity of the signal, electrical signal also should be properly done. Without leakage of current around, and low temperature, like thermal design also should be there, and hydrodynamic environment for launching and recovery, safe launching and recovery, and hydrostatic stability and hydrodynamic efficiency, so that your energy will be optimizely consumed. So power delivery and onboard power supplies we can design, and the vehicle control. If it is a hydrodynamically very efficient, means the vehicle control will be very smooth. Otherwise, we have to put more force, and vehicle controlling will be, maneuvering will be very tough. Salinity, this is actually attenuation of radio frequency signals, which is very important for the navigation and communication system, which works on acoustics. And darkness, we have to depend on the vision systems, and soft seabed locomotion will be a challenging, because once autonomous scoring system, which is for a gas system, this seabed, it was a soft seabed in KGPC and system was sinking. So after that, a system redesign happened on the after landing the system, increased area has made the system not to sink. So in this way, so many challenges we'll be seeing. So coming to different types of underwater vehicles, normally remotely operated vehicle and autonomous underwater vehicle and manned submersible. These three are there. And remotely operable vehicle, it is actually like a deep water, 6,000 meter depth rated, which will be launched like this actually. So this is the remotely operated vehicle. This is called as a tether management system. And this is 7,000 meter umbilical cable, because up to 6,000 meter means we will be having a 1,000 meter cushion. And here tether cable will be there. If it is of 400 meters. So the remotely operated vehicle can go only around 400 meter radius actually. That much survey only can be done. If you come to autonomous underwater vehicle, it is autonomous, no tether will be there, and we can have the long spatio-temporal inspections and all, but depends on the onboard power battery. So manned submersible also actually is untethered, but man in the loop, and it will be running on the batteries. And this also criticality is same, battery operated system. So we'll be having a vehicle endurance. So comparative capabilities, as I told, that remotely operated is endurance. Vehicle endurance is unlimited, because all the power will be supplied continuously from the ship actually. But it is connectivity is tethered. We will be having all of the operation through fiber optic umbilical cable, and we will be seeing all the instantaneously operations from the ship console system. And intervention capability also limited, like manipulator. Intervention means operating any pipeline survey or welding. So the work class ROV will be having the manipulators, and it will be having the limited operations actually. And autonomous underwater vehicle endurance also is limited, because on the onboard batteries, but untethered. So connectivity is also issue. Untethered it is. Intervention not yet matured, but recently China is working on the intervention of the AEV applications. HOV, human occupied vehicle, which is limited, but it is untethered. But intervention, since man is in the loop, we can retrieve any lost items, and we can do some good operation, because you will be directly looking through the viewport and doing the operation. So coming to the deep water ROV ship system, this will be a ship system where we will be having the umbilical with storage winch, and ROV, this is a remotely operated vehicle, and this is our actually ROSUP 6000. It acts as a deep pressure for safe launching and recovery and all. We'll be using a launching and recovery system, which will be installed on the ship actually. And the continuous video and video cameras, the visuals, everything will be through fiber optical umbilical cable. Each and every 1 second we will be getting the data, and tether, that's what. And it will be having many payloads actually, and the thrusters also will be used to propel the vehicle in 4 DOF actually, like forward, backward, lane heading control, depth control, vertical motion. So many things are there in this remotely operated vehicle. And it is also underwater lights, LED lights and cameras are there, and multi-beam sonar. It carries a multi-beam sonar, and manipulators are there, since it falls under world class ROV. So this is a view of the deck systems from the ship actually. So this is the winch, storage winch of that umbilical cable, and this is the hydraulic power unit for the launch and recovery system operation. This actually when we are launching, this pulley will be for paying out the umbilical cable, this will be used. And this is the, it is a launch vehicle holding a satellite. So the position will be like this. When after going to particular location, the ROV will be undocked and the operations will be carried out. So some of other ROVs also will be there, which are like Unmanned launch stations, which is in the near France. So they are continuously working on the dredging for cable laying operations. So ROVs have many applications. And subsea interconnection using ROV. So any pipeline joining and all can be done under the in subsea actually. And deepwater AUV, coming to deepwater AUV, everyone know that Hugin 6,000 meter depth deepwater AUV it is one of the marvel actually, one of the marvel in the ocean history where we are also working on that. I will be AUVs, which is increasing in the range of kilometers, like Seabear and all very limited AUVs actually, maybe 1 kilometer or like that. And then coming to Remus 6,000 Woods holes and Huggins and all 100 kilometer range will be there. And Gavia, Remus 100, everything 100 kilometers. So if you go for gliders and all, it is 10,000 kilometers range is there. But all are Slocum glider and all are autonomous operations. And auto sub long range AEVs also are very important actually. And now coming to underwater vehicle mission plan. Now where our navigation comes. When you are telling in the high level mission planning. So you are going to a particular target location where you want to cover the target location. How you want to land mover pattern or either a circular pattern or only going to that particular location and having a survey. So we should have a mission plan. And then how the path plan, waypoint guidance. Waypoint guidance where every 100 meters we can have a waypoints. So for that, from initial waypoint to other, when we are moving, heading control will be done, auto depth control will be done. So many sensors we can enable it. And what is the control, how much speed of the vehicle we can limit. So in the low level, when it comes, okay, we have given a mission trajectory and we have given how to go forward, backward like this in land mover pattern means, but how we are monitoring. So there the navigation system comes. So continuous real-time navigation means position updation of the vehicle will be given by the navigation system. And the navigation system based on the navigation control of the vehicle, how much speed it has to move. Then control system will come. The thrusters will be enabled in the control and then the vehicle will be updated. And the remaining sensors like altimeter, depth sensor, all the environment awareness will be known by the sensors. So real-time navigation needs continuous update of position, vehicle motion, vehicle speed and the track and its trajectory. So coming to the terrestrial positioning system. So first initially when the vehicle is on the surface, we'll be working on the satellite positioning. First initially we'll be using the position given by the satellites. Like GPS constellation is there, GLONASS is there, Galileo is there. GPS is US based, GLONASS is Russian based constellation, Galileo is European I think, BeiDou is China's, like that, and Iridium. Iridium also, it is a low Earth orbit and continuous visibility is there. When we are going for geostationary, some polar areas we are missing actually, but continuously we are looking, our India means we will be having the geostationary satellites continuously to India. So now Iridium is very important actually because of the continuous position update is if anywhere on the Earth, we will be getting our position and the positioning system of the satellite works on the triangulation principle. So minimum 4 satellites are required for estimating the position of the vehicle on the surface. So underwater navigation and positioning. Why GPS cannot work underwater? I told why, because electromagnetic signal attenuation is seawater is more. As the frequency increases, attenuation also increases. Hence, maybe like 0.5 meter to 1 meter only, I have seen GPS signals working in water. So after that, we will not get any signal actually. And now position estimation using dead reckoning principle. So actually everyone is aware that how the position estimation is done by determining the previous position and by using the estimation of speed and heading direction and the course, like how the course we have given, either a straight line and within the elapsed time. So for what information is required for dead reckoning? Heading is required because at what direction we are giving actually, and displacement with the time. So this can be derived from the accelerometer or velocimeter, okay? Like odometer in terrestrial vehicles. In underwater, we'll call as a Doppler velocity log. Are these two parameters enough? No, we still more need on the vehicle kinematics actually. So we have to understand what are the 6 degrees of freedom actually. So coming to the rotational and translationary motions, these 6 degrees are nothing but rotational means roll, pitch, heading will be there. And translation means is surge in the forward direction, sway in the like horizontal direction, and then like perpendicular to the surge is sway, and heave is in the z axis actually. So these all directions we have to understand. And if you come to this one, forces required for counteraction. So what are the forces required? So forces and moments in the motions in the x direction, surge is x actually. Then these are all called as motions in the x direction, means in xyz plane actually. And rotation is roll, pitch, yeah, I was saying. And then linear and angular velocities. During these motions, what is the linear velocity and angular velocity? And then the position, xyz, and Euler angles. We call as roll, pitch, heading also as Euler angle. And one more also is there in quaternions, where for launch vehicles and all, we'll be using the quaternions. And AUVs also, where two degrees of freedom merge, then we'll be going for quaternions actually. And when we estimate like this velocity of the vehicle, we have to convert from the body frame to earth frame. When we are our underwater vehicle is navigating in a particular place actually, then this itself is called the whatever angular velocity, whatever we will be telling in body frame. When we are telling the position, terrestrial, like position with respect to Earth, then we call it as a navigation frame actually. So how to convert from body frame to navigation is using direct cosine matrix actually. Here we are giving with Euler angles. When you know the attitude data, then we can convert this acceleration or velocity into navigation frame, and then we will be using to estimate the position in latitude and longitude. So this only I was saying. So we have to estimate. So first, initially, we know the latitude means. Then with vehicle velocity in any direction, like north and east and down direction, if you know, then into the sampling time and radius of the curvature, mean radius of the curvature, if you know. Like earth parameters are constant. Rn is nothing but meridian radius, R is the transverse radius, and earth radius is already known as 6378 kilometers, and this is the eccentricity of the vehicle. So using this equation, we can estimate the position of the vehicle in geo coordinates. So normally conventional navigation, underwater navigation algorithm is, inertial navigation system is nothing but it consists of the inertial measurement unit and plus navigation equation, which estimates the position estimation algorithm. This is called as inertial navigation system, and it will be aided with the Doppler velocity log and magnetic compass and pressure sensor. So this alone is actually strapped on inertial navigation system, where the force movement in the x and y z direction linear will be measured by the accelerometer, and angular velocity will be detected by the gyroscopes, and the vehicle in the body frame. So that we will be converting into navigation frame by using the direct cosine matrix. And this magnetic compass also, actually we will be when there is no other sensor, the magnetic compass also will be helping us to get the magnetic heading. And then the pressure sensor is to know how much depth we have traveled. So then to why we are working on the Kalman filter, I will explain actually. So these all computations will be done for estimating the position of the underwater vehicle, attitude of the vehicle, and then direction. So this is actually navigation sensor suite. I was saying about the inertial measurement unit. It consists of triaxial accelerometers and triaxial gyroscopes. Means 3 axes, AX, AY, AZ. In 3 axes, the accelerometer will be measured, and gyroscopes also, the angular velocity will be measured. So we have given some sensor error models where I have used these sensor models to estimate the position, and when we are having a different grades of sensors and all. So these sensor error models are very useful actually. So you already know that acceleration is equal to d square x by dt. When you integrate the acceleration, we'll be getting the velocity. When we integrate the velocity, we'll be getting the position actually, distance traveled plus a constant. So this will be drift, it will be increasing. And when you go with this biostability is very important in the accelerometer scale factor also. So when you go for the navigation grade, tactical grade, in it, like these 4 different grades are there, we have to work on the which is a minimum these things. So if you have the around 0.01 micro G biostability, and then scale factor around 10 ppm, it will fall under the navigation grade. When your biostability is increasing, then your error also will increase, your cost will reduce, but your error will increase. Then we have to depend on the unsupervised Kalman filters like that to filter the noise, the generated noise. So I was saying that from accelerometer, we will be getting the distance traveled, and also from the Doppler velocity log. In underwater vehicles, the Doppler velocity log will be used to measure the velocity of the vehicle with respect to the seabed. So this will be having like this, four beams will be there. So the 4 beams will be this is actually one of the acoustic device, acoustic sensor, where the beams will be generated, and it will be reflected actually. It will be transmitted, and then from the seabed, it will be reflected. So when it is transmitting at one frequency, it will be reflected through the different frequency. So with the frequency shift, we can estimate the velocity of the vehicle. That I am explaining next slide. So this is the one actually. So when the source is different, like delta F, the frequency shift will be computed, and then we will be computing the velocity of the vehicle. And this is also having a sensor model, scale factor, and this is a sea current. So when your vehicle is deployed from here, so we will be having the DVL will be operated in 2 modes, bottom lock mode and water lock mode. So when the vehicle reaches up to the seabed only, like when we are above altitude of 100 meters only, vehicle will go into bottom lock mode, and the velocity computed will be very precise and very accurate. But up to that 5,500 meter, we will be in water lock mode. Like any particles are there, any moving particles are there, vehicle also is moving, so it will be emitting the sound, acoustic signal. So some reflections will come. So, but it will be like a very not accurate velocity, but it is okay compared to like inertial mode. This will be added with some velocity. And we have to add the sea current also, because sea current also will be required to compute the velocity output in the sensor error model. And coming to the gyroscope actually. So now linear velocity measurements are now over. Now gyroscopes, which is used for heading measurement actually. So different types of gyroscopes are there. This also falls under different grades, navigation grade, strategic grade also is there, tactical grade, industrial grade. So this also depends upon the biostability and then scale factor. So when you have like a 0.001, this is actually RLG spectrum, this one. From 0.001 up to 1 degree also is there. So which one we can select for our mission. Like that, we have done a modeling sensor tool, which will be suitable, and how much position deviation will occur, how much position accuracy we will obtain. So based on that, we can select our sensor that we have used for other vehicles, and that also I will be explaining. So different types of gyroscopes are there: fiber optic gyroscope, ring laser gyro. These are all based on the opticals actually, optical sensors, and this works on the based on the Sagnac effect actually. So And vibrating gyroscope also is there. This works on Coriolis effect and hemispherical resonant gyros, MEMS gyros. Normally in our mobile and all, if you see, all MEMS-based gyroscopes and accelerometers will be there, where you can turn your screen. So more you have to turn, then only it can detect. Otherwise, very less if you turn, it cannot detect. So that detection capability only, we are having different grades actually. And even optical gyroscopes measure the true north and immune to external magnetic fields on surrounding materials. So I was saying that fiber optic gyroscopes work on the Sagnac effect. So here, actually one light we will be transmitting from the laser in clockwise and counterclockwise. And based on the rotation, like when the vehicle rotates, these two will collide and give the angular displacement of the vehicle. So this is called as a Sagnac effect. This same principle in fiber optic gyro and ring laser gyro also. So if you go for magnetic compass model, we will be getting the magnetic north. But when you work on this optical gyros, it will detect the Earth's rotation, because the heading the bias stability is 0.005 degree or 0.001 degree. So if you want to detect the Earth's rotation, like Earth's angular rate is 15 degrees per hour. So per second, it will be 0.004 or something. So if you have a bias stability of the gyroscope, if 0.004 or 0.003, we can detect the Earth's rotation. So using that, we true north can be identified. So I was telling about the magnetic compass. So we are also having the magnetic compass in our shallow water ROV, but at poles, normally at at equator, what is the Earth's magnetic field? Around 35 microtesla to 30 to 35 microtesla. At poles, it is 65 microtesla, and the Earth's magnetic field is unevenly distributed. And it is like in contours also it will be there. It is there actually. So if you go for NOVA website and all, we can get more details on the magnetic field of the in the Earth's distribution. But we have to give the declination when you are having a magnetic north. When you are converting into geographic north, we have to give a declination angle that depends on the latitude, because latitude, when you go for higher latitudes, the magnetic field will be rising. So the declination value also changes actually. So if you see here, true north, the magnetic north will be inclined little bit. So the declination angle only I was saying we have to give. And the accuracy of the heading measurement is highly degraded in polar regions. So we have to do calibration, high latitude calibration procedure is there. So when you do, and for limited area, we can work. We can work without with less position error. But when you go for longer ranges, your magnetic compass in polar regions will not work. So coming to the inertial sensor, I was saying that bias, scale factor are very important, and random walk, angular random walk. This is actually a nice output signal from a sensor which is integrated. The integration will drift over time, square root of hours something is there. So this drift also is more. Angular random walk will be more for low like MEMS-based sensor and all. So it is called as angular random walk for gyroscope and velocity random walk for accelerometers. So coming to normal, I was telling that a very Kalman filter is required. So it is a linear quadratic estimation algorithm. It has a recursive algorithm which will be taking all the measurements from all the aiding sensors. If you see this dead reckoning navigation algorithm, first initial position will be from GPS. Then when the vehicle is going in water, we will be taking the aid of the Doppler velocity log. We will be getting the 3-axis velocities in a body frame, and then we will be converting into the navigation frame using our AHRS system. And accelerometer also will be there. This will be giving the forces, linear forces. Whenever Doppler velocity log error is more, then you have to take the accelerometer data for just instantaneous time. So thus, which sensor is more accurate, which is based on its standard deviation and then covariance data, the Kalman filter will decide which sensor to take for the position estimation. So we have developed a modeling tool, I was saying, right? So different class grades we have taken of the accelerometers with the scale factor, bias, and then velocity random walk. And here bias and angular random walk. we have taken, and we have estimated for a circular path actually. If you go for a type A, the position, so when you start from the initial location, we have to end in the again starting location. But for the type A sensor, we are like a position deviation is 30 meters. Again, type B, if we are seeing 90 meters difference, type C 700 meters. So in this way, which sensor you can select, which grade we can go based on your mission, what is that budget, project budget, and based on your limitation. So we can choose our sensors. So this is actually existing underwater positioning system. So it is a FOG based INS, which will be aided with the Doppler velocity log depth sensor. And initially the position will be given by the GPS. And here I was telling about the underwater GPS. This is called as acoustic positioning system that we will be now seeing actually. So acoustic positioning system, how it will work. Normally in our ship, it is called as a USBL transceiver, where the USBL, here an array of transducers, acoustic transducers will be in circular way. It will be mounted like around 255 elements will be mounted, and then the underwater vehicle will be deployed. This will be having the transponder. They both will communicate. So it is a circular array of transducers, right? So whenever the vehicle is here means, so from this acoustic plane, like a traveling will be done, and then this side transducers will be getting the first signal. So then the signal processing in the acoustic positioning system will compute that it is coming from the right side of the vehicle. If here means these arrays transducers will get the first hit, means time of arrival will be computed, and then the direction will be identified. And coming to the range, so from the acoustic positioning system, we will be interested in knowing about the range and bearing angle actually. So range is nothing but travel of time. So we will know the velocity of the sound in water. So and how much time it has taken. That both we will take, and we will compute the range. And this is also called as a beam forming technique. So when we are identifying where is our vehicle, so all the 255 beams will be generated, and it will be searching for the target. So we have different types of acoustic positioning techniques. This is called as a long baseline. What is a baseline? Means the distance between the two acoustic transducers or transponder is called as a baseline. And when you go for the long baseline, it is very accurate. It is used normally in the offshore gas platforms and all. So the long baseline is the distance between them is 100 meters. And based on the triangulation principle, the position of the vehicle will be estimated. If your vehicle is here, everything will be communicated, and I will show the animation how the communication also will take place, how the positioning will be done in different subsystem, in different techniques. And this is a short baseline. In the ship, 3 transducers will be there, and this is our target transponder. So from here also triangulation principle will be done, but in ship more holes will be there, and maintenance will be difficult if you go for a short baseline. This is ultra short baseline. This is only we are using actually in our Sagar Nidhi vehicle ocean research vessel. We are using the ultra short baseline technique. From the past 25 years, we have been using the acoustic positioning system for the unmanned vehicles, and now we'll be using for the manned vehicle also. So here in that circular dome, all the transistors will be placed very nearby, less than 10 centimeters. So the direction of the arrival of the signals will give the bearing angle actually. And this is how the slant range will be computed between the vehicle and ship is c tau by 2 time of flight actually. And here these 2 transducers will be there. When the plane is coming this side, the direction will be computed by the phase difference of the signals. And the variables of see in acoustic when velocity of sound we are telling, so the sound velocity profile also is very important. Acoustic positioning depends on the sound velocity profile of that particular in situ location. So when we are going to deploy the underwater vehicle in water, we'll be taking a profile from our sensor package in the ship. It is already there. So we'll be deploying the sound velocity profiler, and we'll be recording the sound up to up to the deep water, and then we will be taking that profile and we'll be feeding to the acoustic positioning system so that all corrections will be done and we'll be getting the more accurate location. And sound velocity also depends on the temperature, depth and salinity parameters. So these three will affect the sound velocity propagation in shallow and deep waters. So if you see the sound velocity profile, so it initially 1500 meters per second. When you're going to see the seasonal thermocline, it is reducing. And when you're going to the SOFA channel, it is still reducing. After the deep isothermal, same temperature will be there, but again the sound will be increasing actually. So this depends on the location and seasonal variation. And this is the whatever details about the navigation and positioning systems we are working on. And this comes to acoustic underwater communication principles. So communication, when you tell in underwater, it is completely wireless. So we are working on fully acoustics actually, but different types of communication is there. Acoustic, we can go for 10 kilometers maximum, 10 to 11 kilometers, but we are having the key challenges as bandwidth will be less, and it is having multipath reflection and Doppler effect also will be there between the two moving vehicles. Accuracy will be lost, and noise, ambient noise also is very important. And optical, it is like communication region. When you go for a wireless communication, optical means it is less than 100 meters because the light dispersion will be there and scattering will be there, and alignment, line of sight also is very important, and noise also will be there. So magnetic induction, we can go for electromagnetic induction also. Even that is also like less than 100 meter, and connectivity is very important. The sea water connectivity also, but then we can go for very low frequency, but antennas will be very huge size. And radio frequency connectivity like less than 10 meters, and connectivity of seawater is also plays a major role. So we have used electromagnetic principles in our homing and docking system because of the required range and each approach. So based on your range, you can select which communication is okay for you. So normally sound travels in a liquid and air. Air, you know that in our air we are listening the sound, but in water it is 5 times more. Like in air it is 300 meters approximately meter per second. In water the velocity of sound is 1500 meters per second. So sound travels good in water. So we are going to select even, and all aquatic animals also are communicating through sound only, right? But challenging than terrestrial wireless communication, and it is a very we should have a good infrastructure. Means we should have some ports and all should be there, like every 10 kilometers or every 100 kilometers. Some positioning system, some other nodes should be connected through through shore systems. If it is there, it is good. And during World War II, underwater telephone was developed as a communication one, which is of analog communication, single sideband modulation, and the frequency of operation is 8 to 11 kilohertz. And coming to the now, when we are coming to the acoustic telemetry in the latest trend, we are going for digital communication techniques using spread spectrum modulation techniques, and where we can get a good data. But bandwidth is again matters, and data rate also matters. And data and voice communication is only possible in underwater is only through acoustics. So sound propagation in water will be in this like shown here. And I was telling even this acoustic communication also depends on the sound velocity profile, okay, which is space like location dependent and seasonal variation. And how the sound propagates. See, this is the sound velocity profile. When you see here, it is the shallow water range at shallow water up to 500 meters like this. So we'll be having multiple reflections. When you go deeper water, the reflections also will reduce and time of arrival signals also will reduce. Actually, now we are recently working on this acoustic channel modeling using the ray trace tool, which is called as a bellhop. It is like open source available in Python programming language. And I have been working on this for the past 2 years to understand how seabed environment we can give, and how your eigenrays how your acoustic rays propagation will be done up to kilometers, and how much, like we can give the seabed properties also. What is the sediment, clayey or hard rock like that, and uneven sea floors we can give, and we can give the location, sea sound velocity profile, and we can identify the transmission loss of different frequencies in different like transmitter and in one location, receiver in one location. Like horizontally we can work out, and vertically also we can work out. So this is the sound propagation with the 100-meter depth, how the shallow water duct will be there. And depth again 150 meters means here it is like shadow zone will be coming. So normally shadow zone is that SOFA channel. So here submarines will be hiding like that, I heard. Then this is the one more sound velocity profile, and different for different sound velocity profiles, how the propagation is variation I'm just explaining. And here in shallow waters, how the sound propagation like spreading. So in shallow waters means it will be like a spherical, two types will be there. One is spherical and one is cylindrical. So we using these equations, we can identify the transmission loss. So transmission loss in shallow water. So using these all equations, we can get the we can get the range. Okay, attenuation coefficient and absorption coefficient also plays very important role. These actually I have found from one paper, and we are working on this. So these are very important actually, the transmission loss which we have computed using these equations, and we are comparing with the modeling techniques also like bellhop and all. So it is almost matching like empirical equations. These are all empirical equations embedded in the bellhop model. And coming to the ambient noise in ocean, this is the noise spectrum which is available in the standard. When you go for higher frequency, like the ambient aquatic, the fish, which fishes, and then ship noise, everything we can take. If you go for 1 kilohertz, what will be the normally noise? 70 dB will be there. Okay, during the rainy season up to Indian Ocean, how much dB we can take, the noise level. So these and all are required for computing the signal to noise ratio in the communication process actually. So coming to the acoustic channel bandwidth, when you go for very long range, then your bandwidth will reduce. When you go for like a 100-kilometer range, your bandwidth will be 2 to 5 kilohertz. When you go for very short, like a 0.1 kilometer, means 100 meters, then your bandwidth will be more actually. And different types of propagations, which is a reliable path. Actually, this here sender is there, here receiver is there, like ship and our underwater vehicle. This is a very reliable path. Here, if you see the surface reflections will be there. From here, again, B means here, very nearby in shallow waters means you will be having the surface duct propagation. In bottom bounds, both are in bottom means bottom bounds we will be getting. And sender and receiver, both again same level. So we have to choose which is a reliable path for us when you go for deep waters. So signal to noise ratio from the source level and the transmission loss, we can get the noise level also, a noise level and the directivity index. So this signal to noise ratio, when it is greater than the detection threshold, then only your signal can be like analyzed, and it can be listened by the receiver. So this is actually passive sonar equation. If I go for active sonar equation, then 2 times the transmission loss will be the 2 times, because it is like sending and getting received. So these equations are very important when you develop your communication system. So if you go for acoustic communication system, these are the acoustic modems where ship or buoy and in underwater instrumentation. So quadrature amplitude modulation techniques and orthogonal frequency division multiplexing modulation techniques are being used as of now. And this one is the animation, how the acoustic positioning principle. So we have deployed this is actually a transponder, how it will communicate. So this why I am showing is, so the ship always should be in the line of sight. It should be in the operational beam angle coverage. Normally for all the acoustic positioning systems, they are giving like 180 degrees hemispherical. So completely completely the signal coverage can be done at 180 degrees. But in working principle, the side lobes we cannot go for longer ranges. So only 120 degrees only we have to think as a working beam angle. So this one only, that's why I'm showing this. The ship, if it goes away, then we cannot, the signal cannot reach, and position also cannot be computed. When like in our ROV, so from ROV always it is 3/3, so it will be continuously communicating. So this is a tether management system, and here one transponder is deployed. So here also we can communicate the both, and then we can communicate. So this position is already known, and with reference to this position, we can still like compute the accurate position, and the ship will be knowing your ROV, where is your ROV. So multi communication, like positioning techniques, positioning and communication. Now it is integrated in acoustic systems. So the same principle applies. So when it is coming to nearby in this range, then they all are communicating to each other. So coming to the now we are going to just explain, see the underwater navigation and communication systems in NIOT vehicles. So this is coming to the remotely operated vehicle. I joined in 2012 only. Before that, this vehicle was taken into CIOB. I have participated in some 2 cruises for this. So we are having in this equipment, since it is a 6,000 meter depth rated vehicle, we are having a fiber optic gyro based navigation, photonic inertial navigation system aided with a Doppler velocity log, depth sensor, and a sound velocity probe also is there. Instantaneous sound velocity also will be given as an aid to the navigational system, and it is having many scientific sensors and even multi-beam sonar. High resolution bathymetry also can be done, has been done with this vehicle. So this is the technique, this is the scheme which is present here. So if you see here in this position drift without aiding, in a pure inertial mode, without any aid, it is less than 3 meters in 100 seconds, and in 1 hour it is 0.6 nautical mile. It's around like 1.2 kilometers actually. With aiding with DVL, it is like per hour, 3 meters per hour only is per hour will be the position drift. With aiding of GPS, it will be excellent. With aiding of GPS, it will be as good as more good as GPS. So navigation control. So normally the photonic inertial navigation system, this is actually this orange color is the titanium pressure case where all the systems, our electronic systems, everything is placed in this vehicle. And this is the navigational joystick, and this is the ship-based control system. We will be, so pilot will be controlling the vehicle from here, and he will be getting the position update in the system actually. This is the GUI. Here we will be getting the position update, and we can see how the ROV is maneuvered. Actually, after joining, this is one more satellite communication. I just wanted to give this one. First, we have done video streaming. So former director also was chief scientist for this dive actually. This is exploration done in the Rodriguez Triple Junction sulfide site. This ROV seeing the underwater sea image. So we are having in the Sagar Nidhi fleet broadband system modem with the public IP we have configured. And this is a Inmarsat satellite communication. It will communicate with the satellite, and we can see if the same internet connectivity and that public IP is there, we can view all the underwater visuals from our NIOT office. So the satellite communication, this was done in 2013 actually. So coming to the polar ROV, this one I was saying about for 500 meter depth, and this has got many dives. It has done almost like 30 dives. It has done. It is having the 4 degrees of freedom, like forward propulsion, then backward, then lateral, and then heading control and vertical motion. So this is electro-optic, same umbilical cable, but it is of like 600 meter tethered cable will be there, and in this, we wanted to develop, because photonic inertial navigation system is very costly, around 1 crore. We cannot accommodate because space constraints is there. This is very small vehicle of 1 meter length, like that. 1 meter length or what? 1 meter length and 0.9 meter height and 0.7 meter width actually. So we cannot accommodate this photonic inertial navigation system. So we wanted to develop indigenously based on dead reckoning principle. We have developed the positioning system actually. So we have whatever the modeling sensor tool selection we have developed, and we have identified the sensors. And then using the strap-down inertial navigation equation as per the WGS World Geodesic Standard 84, we have updated the position. By first initially the GPS position will be taken, and then the Doppler velocity log will give the velocity of the vehicle when it is maneuvered. And we are using magnetic compass module with the declination and all we have taken care. And by taking the moment, like by integrating the velocity, we will be getting the displacement. Then we will be integrating the this attitude data, and then we will be updating the position. So this has been used on the position updation also. We got in first in Idiki trials, it was tested, and position accuracy was 5%, like for 100 meter travel, we got 105 meters. So it was acceptable, and it is tethered vehicle, so it is okay. And these are the different operations when we went, our team has gone for the inertial torpedo missing in of Vizag at water depths of 90 meter, and this is our position plot. And then DRDL also has called for one more, they have requested for Agni missile actually. This one also was surveyed. And this is our polar application. So our former director was one of the crew member for the polar activity. And these are our team. He is our pilot actually. And when we go to polar region, we'll be not knowing how much altitude is this, because the ice shelf itself is of around so many hundreds of meters height. So we have to go work on the inverted DVL concept. If you see in polar navigation, we'll be using the inverted DVL, where the acoustic beams will be reflected from the ice, and we will be estimating the velocity of the vehicle. So we have done a small case study by keeping all the ice cubes in a small test tank and putting the DVL in the inverted condition, how much we can get the accurate signal, accurate velocity. We have tried, and we have recently published this paper also on the. So when you go for polar region, normally this we have to use the transverse coordinate system, which is alternative Earth coordinate frame. Because when you go in the normal geographic coordinate system, it will be ineffective in the high latitude zones. So up to 65 degrees or 75, up to 65 degrees north and south only, we will be using the conventional navigation system. When it is greater than, we have to use the transverse coordinate system, and we have to get the data. Okay. This one recently only we have I have gone through, and I have worked out on this. So in conventional, the latitude are defined relatively to the equatorial plane, okay, normally, and prime meridian. However, at polar region, the convergence of meridians causes significant distortion, making the standard definitions of direction ambiguous. So direction will be, ambiguity will be there of the identifying the direction. So we have to use this one. So coming to our AUV, it is unmanned vehicle, autonomous vehicle. So here also many scientific payloads are there, and navigation system is like a Honeywell based RLG, and a Doppler velocity log is there, and depth sensor is there. Then altimeter also is there. So this vehicle has autonomy, and then obstacle avoidance consisting of waypoint guidance, and then obstacle avoidance algorithm also is inbuilt. So we are learning many techniques from this vehicle. So these are all the navigation sensor system. Here we are having the inertial measurement unit, Honeywell RLG, and Doppler velocity log. So they have actually, this we have procured from the Kongsberg, Norway. They have developed their own position estimation algorithm. So INS is like proprietary to them. And then but all the navigation sensor suite is same only. So magnetic compass also is there. We have to give the declination value before the start of the mission, because when complete outage is there, we can get the at least approximate position using the magnetic compass. And here GPS receiver will be there, and HiPAP transponder. So in our ship ORV, so Agarnidhi, we are having the Kongsberg high precision acoustic positioning system. So according to that, these are all the transponders we have to mount like we have to use in our underwater vehicles. And coming to the communication, we'll be having the continuous communication. Even AEV also, ship will be following over the AEV during the operations. So we are always in the operational beam coverage, and we should not lose the AEV. But anyway, when we are not having any communication, like for 10 minutes or for 30 minutes, AEV surfaces by dropping the emergency drop weights. And this is also having the Iridium satellite link and radio link, and like a tethered communication also is there. And coming to the operational constraints, I was saying that always ship will be following the AEV. When you are going away means 60 degrees only. That's what I was saying. 120 degrees only will be the operational coverage, and remaining we'll be having the telemetry, very delayed telemetry, and we'll lose the AEV. So this is very critical actually. And Hugin, I was telling completely about all the sensors. And coming to the communication over link also, I have explained through the satellite link we are having, acoustic link completely like telemetry, continuous update of all the key parameters to the ship will be relaying actually every 30 seconds. And we have seen 1.6 kbps acoustic telemetry at deeper waters. So coming to the autonomous vehicle mission plan. So here, whatever I explained earlier, this completely we are using this this is the way we are using for the AEV navigation. So this is actually one of the cruise I participated. So I just wanted to explain this AN32 in 2017 December, it was missing. Our ROSA vehicle also was taken for survey for inspection, but in the given location, no parts were identified. But in 2022, our AEV, deepwater AEV was taken. And here in this area, some calibration was done. But in 2023, after post-analysis of the synthetic aperture data, we have identified many parts are there. So again, we went to the location in the 2023 and by making the mission plan like this. So these are the initial mission plan we are giving through waypoint guidance trajectory. And then we will be selecting as a block 1, block 2, block 3. These are all the camera lines. So when you are telling, these are all the sonar lines actually. Sonar lines will be very long at higher altitude, but camera lines when you are coming, when we take the images, underwater images, 5 meter only altitude will be there. Then only we can take a clear picture. So here we will be assigning like how many lines we are giving, how much distance, what is the speed of the AEV at that location, in that way, in that mission, block A, one mission like that. So we have done everything, and acoustic data telemetry 1.32 kbps we have seen. So these are very critical parameters actually, and this is our GUI of the AEV. We can be continuously seeing what will be the speed of the AEV, how much is the battery charge available, what is the depth, 1.7 meter, 74.2 meter altitude. Sample, just screenshots I have taken. So I was telling the ship always should follow. So the white line will be the ship, like, and every 30 seconds we'll be sending the acoustic positioning for error correction. Any drift is there, the position will be corrected. And this is the motion of the AEV actually. And these are the launching and retrieval of the pics of the AEV actually. And here we have identified the AN32 many parts at 3,400 meter water depth, and even all the images will be geotagged. So around like 2-3 kilometers, all the parts of the AN32 aircraft were spatially found. And coming to the manned submersible, our Matsya 6000 deepwater scientific human submersible. So here, this is a normal general schema. From the ship, we'll be launching the manned submersible, and the manned submersible will be having the many different subsystems. First is the personal sphere and human support safety and support system, and exostructure frame, where we'll be installing the propulsion system, buoyancy system, like main Bala system, and electronics pressure cases, and all the transponders, acoustic transponders, and communication systems and all, and imaging systems like lights, cameras, everything will be mounted. So it is developed for the 3 human beings actually. 3 crew people will be there, pilot, co-pilot, and observer. And here the placement of these in the personal sphere hull, 3 people will be there, and life support will be given. Now it is inside the personal sphere only, and these are all the ballast and trim systems and the propulsions, like these are all the thrusters which are mounted, and the outside fairings will be given for the hydrodynamic shape. So coming to the Matsya vehicle, it is almost like 10-meter length with this 3.2 meter, and height is 5 meter, and it is like 30 tons the weight. And these are all the brief specification. Vehicle speed is 3 knots. 3 knots means 1.5 meters per second. It is designed for that much speed actually, and endurance is 12 hours, and emergency support period is 96 hours plus 96 hours. Total 108 hours. So we have to provide the life support systems like oxygen cylinders, CO2 scrubber system, everything for 108 hours we have designed and kept. And coming to the communication system, it is having a voice acoustic telephone, underwater telephone is there, and data telemetry for sending the key parameters from the submersible to ship mission control center. We are having the acoustic modem also, and acoustic positioning system. It is this Matsya is having redundant acoustic positioning system, and aided with and inertial navigation system aided with the DVL, altimeter, and depth sensor. This actually like a concept of operations. The Matsya will be deployed, then main ballast will be filled, and it will be taken to deeper water. And after going to near seabed, then variable ballast system will be used for fine control. And then while surfacing, we will be we'll be releasing the drop weights, and we'll be surfacing to the we'll be surfacing to the and we'll be parking at 150-meter depth and taking the ship clearance, and then we'll be surfacing, and crew will get embarked. So how we selected in the navigation sensors is now if you see with the time in 1980s to 2020, the accelerometer based on technology evaluation and technology maturity, the accelerometers, quartz-based accelerometers are coming with a very less bias. So we have taken the trend, and we have utilized the latest navigation grade accelerometers and gyroscopes and DVL also. And then opposed angular accuracy, the whatever I was telling, the high precision angular accuracy, they're claiming that it will be 0.01% of the position error. But we have seen at 6,000 meter, almost it is a 60-meter error is there. So this is the developed inertial navigation system. It is integrated with DVL. This is the subsea navigation system. It is consisting of 3 perpendicularly placed fiber optic gyroscopes, which is aided initially with the GPS on surface, and then we will be taking the acoustic positioning system. This is APS-1 and APS-2, and this is the depth sensor. Position, velocity, and attitude of the vehicle will be sent to the control of the vehicle. And these are the minimum parameters, 0.01% of the total distance traveled, circular with a circular error probability of 50%, and heading accuracy is 0.01 degree second lat. And these are the positioning accuracy and acoustic telemetry. They're claiming as 9.6 kbps at 6 kilometer range, but we have seen maximum is like 3 kbps. Navigation position architecture, when you come to the redundant architecture, I was saying, right? So this is the APS-1 and APS-2. We have used the like a reliability tool to design the navigation system, and with only INS-DVL with the depth sensors, opposed USBL like personal sphere system means without any redundancy means the MTBF will be 2.9 years. When you provide with the redundant depth sensor and systems, it will become 3.1. With redundant depth sensor and redundant acoustic positioning system, we are increasing the mean time between failure of the years to 6 years. So we have gone for the redundant acoustic positioning systems for Matsya. So this is the realizer system. Acoustic positioning system 1 is already installed in the Sagar Nidhi, and relative transponders. These are all the proprietary protocols. Both are independent, unique to each other. Other protocols will be followed, but basic is spread spectrum only, but they are having their own protocols actually. So only one make can speak to one make, only that make actually. So this is acoustic main positioning system, and second redundant one is from Evologics we have procured, and this is the mission control center, and this is the INS DVL which will be placed at the center of gravity of the vehicle, and these are all the depth sensors. And we have realized like for 500-meter depth rated underwater acoustic telephone from Triton submersible, which they have used subsea imports. And for L3 from L3 Harris, we have procured the underwater acoustic telephone for 6,000-meter depth. So these are all the realized navigation system, navigation, positioning, and communication systems for the Matsya 6000. And also we are having the Iridium satellite modem, because during the emergency, when Matsya sinks, then we are having emergency rescue pop-up buoy. It will come with the satellite modem, and it will give the location of the Matsya vehicle. Then we can go for recovery operations. We can plan recovery within the 96 hours. And recovery challenges. Actually, one of the test case, our former director was telling me during all sensor outages, what will be the approximate position of the vehicle when Matsya surfaces. That one we have to estimate. And what will be the nearly likely probable position also we have estimated. So with the different DVL grades, with the different inertial measurement units of like accelerometer with strategic grade, navigation grade, we have computed. And with the different opposed grades also we have computed. And so we are taking the sensor models actually. So our inertial measurement unit, depth, all the sensor models will be taken, and the position estimation algorithm will be done. And Monte Carlo simulation we are doing for like estimating the probable position. So we are getting around like 200 meters plus or minus with INS position drift. Purely INS position drift is 3 plus or minus 0.25 kilometers. With DVL aid means different actually. So this is the sea current velocity which we have measured with our ADCP in our Indian Ocean Basin. This one we have used for the analysis. So this is the logic which we are running for the estimating the probable location of the vehicle. So we can see that INS position drift with the DVL aid only during descent and ascent, it is 3.1 plus or minus 0.25 kilometers. And with the pure inertial means, it is 6 kilometers plus or minus 0.25 kilometers. If at all we are having the INS position drift with the USBL aid means, it will be approximately like 42 meters with grade 1. With the grade 2 means around 106 meters when the vehicle is at 60 degrees from the ship. And acoustic data communication we have tested in the like in very shallow waters, like 25-meter depth we have tested, and we have got around 2.7 kbps data rate. And this is the acoustic telemetry we have designed for Matsya. Like every 30 seconds, we will be sending all the key parameters from the Matsya to the vehicle, to the MC's Emission Control Center. So we have like framed 48 bytes, like 64 bytes only is the maximum data frame length. So accordingly, we have accommodated all the sensors data, and we have we have transmitted, and the performance was very good during the last harbor trials. And this is just a glimpse of the GUI. And this is the Matsya 6000 operations with the syntactic foam, available syntactic foam. The vehicle was deployed up to 6-meter depth. And this is the maneuvering. So navigation system also was measuring, and around 40 meters, the vehicle has been maneuvered in forward direction, around 30 to 40 meters actually. And physical, like coming to subsurface communication and underwater communication, if you see underwater telephone at 6-meter depth and all, the seabed was very clayey. So the performance was very poor, actually, very feeble voice only we can listen. So we have gone for the VHF surface voice communication by increasing the range, and by putting the VHF antenna in the line of sight, we were able to get the voice communication, and we have done 5 mine dives. So recently we have developed like AML based operational digital twin for Matsya 6000. So here we will be getting all the real-time data through the acoustic telemetry. Still it is in the progress. So I just wanted to bring what are the latest technologies we have been working on the Matsya 6000. And so many like mathematical models, data-driven models will be there. So data from the physical sensors of the system in real time, it will be taken to the digital twin, and based on the model, it will be estimating, like decision will be given by the digital twin to the pilot. So in emergency system, a pilot will be like panic at the time, decision support aid will be really helping the crew members. So we have developed a digital twin for emergency battery system, life support system, positioning and propulsion. Coming to the position, vehicle loss position should be known, and water current profile also we'll be having, and the drop weight status, because buoyancy of the vehicle varies the ascent velocity of the vehicle. So by taking these three inputs, we will be estimating the real-time position and surfacing location after ascent motion. So this is a small work we have done actually. So coming to the last noun position, latitude and longitude we should give, and what is the current depth also we should give, and what is the depth, how much drop weight is pending, and what are we are going to use. Everything we have to input, then it will give how much time to reach surface, and what will be the probable location, how much 500 meter away. So a ship should be ready for fast recovery of the crew members. So this is updation. And I was telling that a bio-inspired homing and guidance techniques also we have developed. Here also, positioning is very important because your docking station is almost like 1 meter dia. So the position accuracy of the AEV when it is docking towards, like homing towards the docking station, is very important. So here we have used short range homing guidance only. I was explaining, right? Electromagnetic guidance we are using, and vision also we are using. So the vision is we have put LED strip light, and by illuminating the docking station, on the camera inside the AUV will detect that illuminated docking station, and using our imaging principles and the AUV will be guided to move towards the docking station approximately. And first, initially away, like if you know that in underwater cameras and all will work only up to 5 meter range. So beyond that, we have generated the electromagnetic field for like 10 meters, and then we have put the magnetometers on the AEV, and it will measure the magnetic field, the artificial magnetic field, by nullifying the Earth's magnetic field actually. So it will measure the actual like generated magnetic field and move towards the docking station. And we have we have tested in our acoustic test facility, and the operations were very successful, and it is very reliable. And some demanding needs actually. So see, Dornier aircraft was missing, then MH Malaysian Airlines also 370 was missing, and AIM-32 also was lost. So these and all needs. And recently, tourist submersible failures like Titanic tourist submersible went missing in 2023, and last 2 days back, Egyptian tourist submersibles also sinked due to mechanical failure. So here and all, we have to have a strategic demands for the swarm of AUVs like covering for inspection, and locating all the missing flights. We should have many still more infrastructure, more technologies to be evolved, and even in polar under ice navigation, and we have to increase the vehicle energy duration. Coming to the gliders with very less propulsion, because that is a buoyancy system, so it is going for 10,000 kilometers, and also still more we have to work on this. And these are the little glimpse of like upcoming techniques. We are also going to work on the AAV swarm. My colleague is going to work on the AAV swarm. And here also, when you come into swarm, energy endurance and communication and position navigation is very important here also. And coming to autonomy, though we have autonomous underwater vehicle, we have to still work on the autonomy indigenously for making intelligent vehicles. And coming to autonomy, it works like a navigation autonomy, intervention autonomy, and energy autonomy. So navigation autonomy, anyway, sensor fusion and obstacle avoidance, waypoint guidance, and the vehicle prognostics, like situation awareness, will be is very important. Coming to energy autonomy, this residual energy battery management system, and the propulsion, like efficient propulsion when onboard storage energy is very less. So we have to work on that based on the environment condition. And intervention autonomy to carry out like autonomous vehicle means when it goes and it can do some building of the pipelines and all in subsea, it is really useful. This still we have to explore. Yeah. Amir? With this, I am closing my talk.
Yeah, thank you, Dr. Jyothi. Yeah, so I'll request Professor C.S. Kumar to, maybe request the chief guest if when it's finished.
Yeah. Thank you, Dr. Naga Jyothi. It was a very fantastic exposition that you have given. Very amazing. I'm sure it has enthralled the users also. So let us hear from the audience if they have any questions, since it's open for Q&A. So I will request the audience to start putting their questions in the Q&A box. I mean, they can type in the
The audience can type in their questions in the Q&A box.
So we are open for taking questions. Please go ahead and put your questions in the chat box.
Can I close my PPT? Can I stop sharing?
Yeah. You can stop sharing.
You can stop sharing, but if the Q&A requires you to have the PPT,
Yes.
you might bring it back on. Okay. Yeah.
Meanwhile, we have got a few observations in the chat box. Perhaps Prem Kumar Krishnan has complimented the NIOT scientists for bringing out the indigenized underwater navigation and communication system for unmanned and manned submersibles. He appreciated that the speaker has landed from space to ocean tech, and he sort of appreciated that you presented the fundamentals. And he's also felicitated the chief guest. Welcome, Dr. Manukurla, sir. President of INA has also joined us. Welcome, sir. And he has also appreciated Dr. Ramadass. We know his leadership in ocean technologies, and Mr. Krishnan has appreciated that also. And Mr. Josman Das Gupta was the previous president of INA. He has also appreciated and thanked the presenter for a comprehensive presentation. Bhupesh Thakur has also told a wonderful presentation and a very informative presentation. These are some of the comments that we have received. Just reading the comments. Now it's open for Q&A. Meanwhile, request with the permission of the session chair, whether Dr. Manukurla.
It's a pleasure to have Dr. Manukurla also present here. Please, Dr. Manukurla, your comments, observations, questions.
Right. At the outset, let me thank Professor C.S. Kumar and Dr. Ramadass. We had a wonderful presentation. Madam has to be really appreciated. It was an exhaustive presentation. She has actually ventured into all underwater systems and the navigation, what all type of sensors. Exhaustive presentation. Probably we should have made it to session 1, session 2, session 3. Three major areas. And as deep as 6,000 meters, she has taken straight away. Okay, good. I think it was quite informative, and it will give a lot of what should I say, interest for the youngsters who have participated. One has already called me and said it was a very good presentation, sir. We want to do PhD in this area. So I told the right people are there. You can straight away register with Dr. C.S. Kumar. So lot of interested parties.
Thank you. I think we are here to answer, to felicitate more Dr. Bala. Naga Jyothi.
Dr. Bala has done this wonderful job. That's what I wanted to tell. It's nice to know that, we have, young professionals coming up with a lot of information, a lot of knowledge, and they are also spreading that knowledge. This is very good. I think we will have to have a, technology savvy youngsters, technology savvy ocean technology aspirants in the coming days to come to harness all those wealth that's lying around us and to sustainably explore all those wealth that is out there. So this is a welcoming trend that is happening, and I appreciate actually Dr. Bharadwaj Srinivasan for identifying the right people and the right topic at the right time. We are fortunate to have Professor C.S. Kumar and Dr. Ramadass with us, along with other senior members. We had good participation also. I think students of IMU are also there in the hall watching it. So they also are appreciating. Very good. Over to Bharadwaj.
I think we got one question in the Q&A box, Professor Kumar. We've got one question in the Q&A box.
Yeah,
Wish we can
this.
invite him to the panel and ask him to ask verbally also, sir.
Yeah, please go ahead and invite the person. I'm unable to make out. They're mostly comments, I guess. Okay, but please go ahead. Invite them to the panel and let them ask questions.
Yeah, Mr. Shiju John, we have added you in the panel. You can unmute and go ahead. Yeah, sir. Yeah.
I'll read the question. A wonderful lecture is appreciated the lecture and appreciated the NIOT team. And what he's asking is, does the DVL you're using automatically switch between bottom lock and bottom lock? Is it doing it by altitude switching or any other method? That is the question.
Sir, actually, the DVL, whatever we are using, will be in the PD6 format. It will give the waterlock data and bottom lock data. Whenever it is seeing the sea bottom, it will give the valid bottom lock data. So, based on the validity of the data, we will be taking the whichever is good.
Is the switch already programmed? That is what I think.
Yes, sir. Previously, very olden days, that switching over was there. Now it is matured.
Thank you. Was one question. Yeah. Some more questions. Yeah, there are a lot of appreciations, rather.
I can see many appreciations. Yeah,
Many
that's right. I mean, obviously, this kind of talk will excite everyone's response in the appreciative mode.
With the permission of the chair, can we ask the chief guest to for his appreciation on the topic, sir, with the permission of the chair?
Yeah, okay. After that, I will give the summary. Okay, please, Dr. Ramadass, it would be nice. It is from my side, I would say you really gave a good chance for her to bring the views. So now please take over and give your suggestion, your comments on this.
Yeah, Dr. Manu Kurula, Professor Kumar, Dr. Bharadwaj, and my senior colleague from NIOT, Dr. Prem Kumar, and Dr. Jyothi, the VIP of today's meeting, and the invitees, participants, and members of the association or institution. Very good evening, and it has been my pleasure to be here today. And I congratulate Dr. Bharadwaj for organizing this lecture, first of all. And of course, about the talk, I have nothing much to say now, actually. Jyothi said it all, actually. I'm proud to be a former colleague of her, and incidentally, she has been my student during her PhD, and we did a lot of work together. I used to give her only 1%, and she used to make it 100% later. And of course, she gave me the credit also for that. So I don't say I can thank her, but I bless her. Okay, so it was a wonderful talk, Dr. Jyothi. Okay. And I'm proud of you. Okay. And quickly, I don't have much to say, but I say that actually, I'll not say much technical things, but we always say Earth is covered with 70% of water, but it has become a cliche. But imagine if 30% of the land in which only 5% is habitable, if it can give us so much for so many years, okay, in spite of our use and abuse, and imagine what 70% can give us if we judiciously use. That is a power. We are exploring space because we can, okay. As Professor Kumar was saying in the initial chart, actually, We are exploring the space because we can, okay? But I don't know how much we get from that, at least except the satellite communication and remote sensing. I don't know how much material things we are getting from that and whether we'll be getting it in the future also. But our backyard ocean can give us so much. For 2000 years, actually, space exploration started even 200 BC and all, but real exploration started. We started looking under the water only in around 1800 years, actually, 1800 AD, when I think Charles Darwin went on a ship, actually, Challenger, actually. I think Discovery, I think they just in 1800 something, actually, they went there. So we delayed it, actually. Why? Because if you have, for example, if you want to see Saturn rings, you have a powerful telescope, you can go to your terrace and see. And if you want to see what is below 10 meters of water depth in Bay of Bengal, where do you go? So it's easy, okay? And you can control Mars rover sitting from here, your office with a delay, but you can't control what is below 50 meters. It's impossible. Electromagnetic waves don't travel in the ocean, so we have to use sound. Sound is 0.2 million times slower. It's lazy, it bends, and its bandwidth is very small. So you cannot see. You have to use sound for seeing. That too, it's not so good actually. So it makes a challenging environment for us. It is pitch dark beyond 50 meters. You don't know where you are. Your GPS doesn't work. Your radar doesn't work. So what do you do? And navigation is very important. Even on the Earth also, actually, when they started going on the ships and all to reach India and all, navigation was a problem. Okay, latitude was okay, fine, but longitude finding was a challenge. I think modern clocks and all are actually, they came up only because of these things. Even now, actually, if you go to space, again, it's a problem. But you have star navigation, star-based navigation, constellation-based navigations, inertial navigation works. There are so many things are there. But in ocean, none of these things work properly. Even inertial navigation, as Dr. Jyothi was explaining, it accumulates errors. And that too, as it says, actually only when there is an acceleration, inertial navigation works. If there is a uniform velocity, actually it goes haywire. So it's an enemy of navigation. So what do you do in these things? So you can't keep on accelerating your vehicle. Okay, so there are so many problems in that one. So I say that navigation in inner space is much more difficult than navigation in outer space. We have to have so many combinations of these things. But imagine navigation and positioning is very important. Europeans colonized us only because they could navigate properly. That's why they realized the importance of that one. As soon as they invaded a country, they used to survey the whole country and lay telephone lines and railway lines and all, not because of love of anything, but because they want to navigate, they want to communicate, then they can actually dominate. So if you want to really dominate the oceans, if you really want to get something from the oceans, you should be able to know where you are and where you are going and how you are going. That is the power of navigation. That's what Dr. Jyothi told us today with her talk. Okay, so it is not a simple topic, actually. As Dr. Manokurla was saying, actually, many PhDs can be launched, okay, in this one. And Dr. Kumar, Professor Kumar is not new to this, actually. He has done a lot in this one and acoustic communications and all. So definitely this can spawn a lot of PhDs and all. And we have achieved a lot, but still there is a lot to be achieved. And we have to do something like whether we can have some kind of algorithms for self-calibrating our INS. Maybe we can create, there are some algorithms, create accelerations, create turns and all, 90 degrees turns and all, keep calibrating, especially with high endurance AU is being launched by Indian Navy. Okay, I think this is very important aspects. And another thing is whether we can have permanent buoys in the world, actually, in oceans like satellites and all, whether we can keep on communicating, actually, giving the positions and all, that we can have like a satellite thing and all. There was a project actually by France sometime back, actually. But I don't know where we'll be giving the signals, because who will be using them? Submarines and all obviously cannot use actually this kind of signals, okay? But anyway, for scientific submersibles, at least we can have this kind of communications. And we need to have alternate navigation systems. In fact, Dr. Maisel Dr. Bala Jyothi and I and Dr. Vedachalam, we authored a paper in Nature about the magnetic navigation before I retired. Actually. So that can be taken seriously. And of course, swarm robotics, communication between them, and then position keeping, vision-based navigation system. There are so many aspects that can be explored. But first, we should know the importance of that one. Then actually, some people are driven by the importance, some people are driven by the difficulty of the problem. And this is one topic which has everything in that one actually. So I urge the participants to take a leaf out of Dr. Bala Jyothi's book and then start working on this kind of techniques. Actually, the more the merrier, because the more people work on it, the more we get actually. And this is where one of the fields where India is not lagging very far behind. Actually, maybe Dr. Bharadwaj knows better actually, but we may be in the forefront as well actually in this one. So I think we should take it seriously. And I really appreciate this institution of Naval Architects actually bringing out this kind of a very important topic in the other part of this webinar actually. Thank you very much. These are my views. And I once again congratulate the organizers, and I thank the chairman of the session, Professor Kumar, for his deft handling of the seminar. Thank you. Bye. Sir, you're muted. We can't hear you.
Yeah, it's so nice of you, Dr. Ramadass, to give such an apt, a nice summarizing and bringing in new thoughtful views on this and putting a lot of new things in perspective. It's what was more than the things that were covered in the talk. It's really nice in that sense. And I know I have the duty of summarizing many of these things, but I think you have done a good bit of summarization, so I will not do that so much. Instead, I'll first give my very quick comments, suggestions, and maybe a couple of questions also I may throw it in this process. First of all, I mean, this was a fantastic topic which the Institute of Naval Architecture has brought to this forum and made it through webinar. I'm not sure whether it is a part of their charter, because the naval architects are more into designing ships, designing submarines and designing all those kind of things. But when it comes to doing this kind of navigation, control, acoustic communication, and all that, it is way beyond what you can just see naval hydrodynamics, naval vessel control, and all that. You, as a rightly put through in this, you need to know where you are when you're navigating. And it is dependable and easy when you work, somewhat dependable. And as you rightly, as Dr. Ramdas also rightly mentioned, when we are able to navigate on the surface of the Earth, there were ships which were using stars as guidance, and even GPS was not there, and compasses, and you could do a lot of things to locate yourself and find your way on the Earth. Still, there were challenges. They could not find where India is. Everybody was eager to know where was India, and there were different streams which took place. But yes, on surface it is quite challenging, and over the years it has perfected to quite an technology with using satellites, GPS, and all that. But the moment you go underwater, and this talk was entirely about that, all that has to be revisited. In fact, not just revisited, we are in an unknown, uncharted domain. They literally, as rightly pointed out by the speaker, nothing is possible to be used. I mean, she has given so nice expose of what the different frequencies that we use for communicating. Nothing can be used beyond a few hundred meters, maybe a kilometer if it is acoustic, but everything else is much less than a few hundred meters. And conventional visual and other things are below meters. So it's almost impossible to use the conventional, well-known techniques on which so many years of research has taken place. But underwater, you are in completely uncharted territory. And this talk, the way Dr. Nagajyoti has given, not only covered the systems, but brought in all the finer aspects of it in such a detailed manner that I must also admit that it was a new learning for me. Okay. We did start working on it way back when we were doing the first AUVs. And at that time, our range of operations were not very long. Nobody was thinking beyond a few 100 meters. So, but yes, geospatial locationing was important. So it depended on the GPS and then go a few meters around depending on whatever underwater navigation systems were giving, acoustic systems. But now when you're talking of what NIOT is doing, where you're talking of several thousands of meters going down, navigating, and maybe several thousands of meters going in the horizontal direction, you need very good navigation systems. Okay. And that's where I think this talk gave the foundations for that to the to the attendees. I'm sure several are even at my age, even though I'm here, I acted like a student. Okay, it's a student. Students will definitely be benefited from this. I must thank her for bringing in this level of details. I really appreciate that aspect. And I was actually surprised, and maybe it's not a question anymore, but I was really surprised that at some stage, when she particularly gave all those details, we are aware that speed of sound is not constant in water, it is depth dependent, factor dependent, and it makes it even more challenging as a consequence of it, which is an essential element in all communication systems. Um, when she was telling about the Matsya 6000, and it's nice that this talk brought out Matsya 6000 details also. I believe the members of NIOT team are here. It's a very national pride now that somebody is working on that, developing these. I was actually surprised that there is something called, even for this navigation NPC approval, navigation positioning and control, there is
Communication.
communication. I'm sorry. Yeah, communication. There is a DNV approval for that. I mean, I didn't know this. I think this, that DNV gets into this aspect also, and particularly if it is underwater. Ships I can
Yeah.
understand, but underwater, do we regularly
No, sir,
operate any
actually,
common vessels like that? It's a surprise. Maybe you can throw some light on how DNV has come into picture here.
yeah, yes. Actually, it is a mandated system. So we have to use design from, and we have tied up with DNV. We are married, NIOT married with DNV for the Matsya project. So all the system design from the design level up to the realization, it will be certified by the DNV. We cannot just for unmanned vehicles, we are commercially off the shelf cameras and all we are buying, no, sir. But for the Matsya, it is not like that. We have to follow their guidelines, any component we are buying, it should be 1.2 times the pressure tested. Then only we can place because it may lead to any damage or any pressure tolerate if it is not there. So some failures will be there. Water entry may be there. So these are all the failures we have seen. And since it is a mandated vehicle, Matsya 6000 is certified by DNB. So all the products in that will be certified by DNV, like all subsystem levels. Now, when deep water vehicle comes, the personal spear will be titanium, this one. As of now, it is 500-meter depth rated. It is MS only. So that also will be certified by DNV. From the manufacturing of the titanium spear, titanium frame, everything will be certified by DNV.
Oh, that's interesting to know. Nice to point this out, but DNV has a group to do all that analysis and say certification to that level of depth for all these components.
Yes, sir. Yes, sir. Yes.
Yes,
Germany and Norway, not in India.
Okay. So does it mean that all our vehicles that we make underwater ships, I can understand it's mass produced or quite close to mass produced, but underwater vehicles are very few, much fewer. They also go through the same rigor of certification. I can understand safety is very important, but then unmanned ones, yeah.
Even the Titan man submersible, they have not followed any guidelines. So only the failure was seen actually.
So while these are mechanical failures mostly,
Yes,
but
yes, yes.
or failure criteria, a communication system failure or a navigation system failure, how do you ascertain that? I mean, are there any standards for that?
No. For that, no standard, sir. We are only that's why we are following a reliability analysis. We are using the this GRIF software actually. Graphical reliability interface, this fault trees will be providing each component failure data, like mean time between failure, and we will be seeing only with only one single system what is the probability of failure. Then when we add redundancy, where we can improve the MTBF value. So we can reduce the probability of failure and we can increase the mean time between failure. So in that way also we have done where redundancy is important, because acoustic systems are unreliable, no sir, sometimes transducers unreliable. So we have added the redundancy and increased the MTBF.
Thank you for enlightening me on this, and I'm sure the audience will also benefit from that. This one. Yeah, I really don't have much to add. Everybody has given very good accolades. From my side also, excellent accolades. I really appreciate that there is a generation following this up. I was aware for sure that very few people were taking up these challenges. And thanks to NIOT, and this project and Dr. Ramadass, and this combination that you sought in this INA has given for this talk, that both of them being present, so all aspects could be discussed nicely. This is a very nice thing that has happened today. I really appreciate from this, and on behalf of all this audience and others, from my side, not only the appreciation, I thank the speaker profusely. I think we should give her a very big hand for this talk. Okay, yeah.
Thanks. Thank you very much.
So over to the INA, this one for. If there's anything more I have to do, please let me know.
No, sir. Thank you, sir. Thank you, sir. It was a great talk and a great evening. Very good weekend where we were enlightened. Our President Dr. Manukarla was mentioning, it was encompassing 3 different distinct areas, but as well as seeing how it gets together as a whole. Excellent talk. Now it's also my pleasure and privilege to give the vote of thanks. First thanks is to Dr. Ramadass, who came and joined us as the chief guest. Thank you, sir. We know your expertise and your depth of knowledge. Thanks for joining us and also giving your views. Yes, the speaker has covered, but your views also added to a few more points, like the experience in magnetic navigation, which was covered as a part of the lecture, but your views were very important. So thanks for joining us as chief guest.
My pleasure.
Professor Kumar, I conveyed this slightly earlier, but then Professor Kumar had some other official engagement. So in spite of his official engagement in a totally different city, he still held to his promise and joined us to chair the session wonderfully well. Thank you, sir, for chairing the session and giving a very good summary. We also noted, and during his summary also, he could prompt a few more extended discussions, which were adding to the knowledge of what was conveyed. On my thanks, all of us have appreciated Dr. Jyothi. It was a very comprehensive lecture, one of the best lectures I can tell of INA, which we keep doing. Thank you, madam. It was a very comprehensive lecture. Thank you for accepting our invitation and giving a very excellent talk. These lectures are being done every month under the guidance of Dr. Manukurla, the president of INA. Thank you, sir. You have created a system where this happens, and the INA team. And my thanks is also to Dr. Vedachalam. I actually talked to him around a month back when I just asked, I'm having something in mind. I want somebody to talk on navigation and communication. He guided me to Dr. Jyothi. So my thanks to Dr. Vedachalam, who connected me to the speaker. Thanks. And INA Executive Council, Senior Secretary, Technical Secretary, and everybody. And Mr. Amir Ahmad, who is our IT Secretary and Organization Secretary, who was behind all these things. We have him continuously engaged and ensuring that we are seamlessly connected. And the INA office. And my thanks to around 45 participants. These are basically the numbers who have registered. Actually, Dr. Panukurla was mentioning, we know that in some of the institutes, the students, basically it's one name, but the students entirely sit on a hall. So with that, with the messages that we are getting, we had an audience of maybe around 90 today, considering all the students were logging in with one ID and a very popular lecture. So we thank all the participants who have joined us and made this successful. Thank you, ma'am, and have a great week. Have a great weekend.
Thank you very much.
Thank you all. We can close the lecture and have a great weekend. All of you have a great weekend. Thanks.
Sir, we would like to invite like everyone to NIOT to see Matsya vehicle.
Yeah, sure. I mean, that's an open
Professor
invitation,
C.S. Kumar sir also. Yeah.
which is to all the audience. I'm sure NIOT will
Me too,
foster.
Jyothi.
Sir?
Yeah.
Me too, Jyothi.
Yeah. You're always invite. You are NIOT, sir. That's sir. Yes.
That's
An
actually
open
very
invitation to
nice
all the
to
audience.
hear.
We'll certainly do that. Thank you. Thank you, ma'am. Thank you.
Thank you very much, sir. Bye, sir. Bye.
Bye. Bye. Thank you. Have a great weekend.
Thank you. Yeah. Good night.
Thank
Good
you,
night.
sir. Thank you.
So with your permission, can I close, sir?
Yeah.
Yeah, please.